yet, but so don't move it, obviously.
Whose idea was this?
It's mine. I told somebody I was going to do it. Okay, I'm not going to make it visible to you then. I may send a link to you. All right, so we're going to continue this week with complex integration. We've finished pretty much complex differentiation, but of course we will come back to it. But before we start, we have the inspirational quote of the week. This time it's from the historian of maths. Maths is not a careful march down a well-cleared highway, but a journey into a strange wilderness where the explorers often get lost. Rigour should be a signal to the historian that the maps have been made and the real explorers have gone elsewhere. You are all real explorers. Okay, let's move on then. So there's quite a lot to get through today. Not many proofs, but a lot of concepts. We're going to do integration. I'm going to kind of link it a little bit to your Lebesgue integrals, but importantly, we don't need the power of Lebesgue integrals for complex integration, not necessarily. Okay, so we will generally be working with the Riemann integral, or an equivalent of the Riemann integral. Okay. So let's start then. So we'll define three different types of integration. Wait. It's too much to remember. So we'll define three different types of integration, and just kind of look at what each of them does. Okay, so they're kind of building up to what you have seen before in the first half, i.e., stuff about parameterizations and how you kind of do path integrals and stuff like that. Okay, so we'll talk a little bit about that. Okay. So, all of the stuff that you've learned about parameterizing curves will be important in this lesson today. Okay. I'm going to link it all to vector fields a little bit. Okay, but that is simply a tool to avoid having to prove all of the stuff that you did with vector fields. So stuff like how if you change the parameterization of a curve, then the integral is the same. If you swap the direction of the curve, then the integral should be negative of what it was before, and so on. Okay, I don't want to pre-prove all those in the complex domain because you've already proved those things in the real domain, and it's easier to just say, look, it's pretty much the same thing, and then you get all of that machinery. Free with it, really. Okay, and at the end I'm going to look at basically a massively important theorem called Cauchy's theorem. All right. So in complex analysis, what happens is you've got this kind of mountainy thing here. Okay, you've got a mountainy thing. Okay, and at the top of the mountain. Okay, this is the mountain. So imagine that basically at the bottom of the mountain you've got this lovely scenery. This is grass and trees. Let's do a tree. Okay, stuff like this. Okay. Whatever. I can do it. I can do it. And the idea is that at the moment we're kind of climbing up this mountain here. Okay. Yeah, little person. And at the top is Cauchy's theorem. This is called Cauchy's mountain. Okay, this is Cauchy's mountain. All right, and at the top of Cauchy's mountain is Cauchy's theorem. And the idea is that this is how complex analysis works: is that once you get to the top and you look at Cauchy's theorem and you have all of this thing, turns out there's all this amazing scenery that you can see from the top of it. Okay.
I put calcium might keep you down.
Wow.
You have to climb up again.
Okay. So this is where we're heading. So Cauchy's theorem kind of allows you to really, really understand what complex analysis is, and importantly, why it is very different to real analysis. All right. So we are heading to the top of the mountain today.
Calcium on top, yeah.
And it is an important thing. So we've got reading week next week, but after reading week, we're going to prove Cauchy's theorem. So we have an entire session based on proving Cauchy's theorem. Okay, it is very important, so it's worth seeing it. Okay, and you're in your third year, you know. Okay.
10 pages of proof.
Yeah, that's right. Yeah, 7 pages of proof. Yeah, but it is this amazing. It's amazing proof. It's really clever, and it's worth seeing. Okay. All right. So we're going to start with something fairly innocuous, fairly straightforward. We're going to start with a function for a moment that takes a real interval. So AB is just a real interval, and it maps. So this is a subset of the real line. So it maps that real interval into the complex plane. Yeah, into the complex plane. So you've seen things like this before. Okay, they're a bit like paths. Yeah, paths in R2. But this is the kind of thing that we'll look at. So the way you define the integral of a function like this, okay, is by doing what we've done before, by rewriting f in terms of its real part and its imaginary part. Okay, so the real part we always call u, and the imaginary part we always call v. So suppose f of t can be written as u plus iv of t, okay, and these are then functions. So u then is a function from a, b to the reals, and v is also a function from a, b to the reals. Okay, so they're just real valued functions, like basically normal functions, right? Then what we do is we define this integral. Okay, so when we say the integral of a function like this is what we mean. Okay, so the integral of a complex valued function is the integral of the real part plus I times the integral of the imaginary part. Okay, which is exactly what you'd expect. I mean, this isn't some sort of clever trick. It's what, if I asked you to define something like this, probably you'd end up doing something like this. Yeah. So this is what we will define. So this is importantly a small example of a function that maps a real interval into the complex plane. Okay. So for example, what we mean by this is, if you look at the example in the notes there, I can't remember what number it is. Oh no, it's not. This isn't in the notes. I remember now. So if you want to work out an integral like this, okay, then note how it's the real part of the function is t squared. And the imaginary part of the function, let's actually write it like this, is minus 3t. Okay, and you put the I out there. Okay, so the imaginary part is minus 3t. Yeah. So see, I mean, although it's not saying a great deal here. All I've done is I've split this thing into the real and imaginary parts. So the integral from 0 to 2 of t squared is what?
T cubed over 3, which is 8 over 3 minus, 8 over 3.
Yeah, 8 over 3. Okay. What about the integral of minus 3t from 0 to 2?
Minus 3t squared.
Yes.
12 minus 6.
Minus 6. Okay, minus 6. So this is 8 thirds minus 6i. Okay. So that's all it is. It's just you just integrate with the real part and then you integrate the imaginary part. Yeah. Okay. So integrating a function like that is relatively straightforward. Okay. There are things that are important that we should check. Okay. The standard stuff that you should check is whether or not the integral of f plus g is the integral of f plus the integral of g, but it is. Okay, but there are other things that are important, of course. We should check that the integral of a constant times f is the constant times the integral. Okay, and I'm not going to do that, but you should check that. Okay, it's a matter of writing the complex number c as, I don't know, d plus ei or something, or x plus iy or something, and expanding all of that and just making sure that it is the left-hand side is the right-hand side. Much more important is the triangle inequality. Okay, so in real analysis you see this used quite a lot, this triangle inequality. Okay, and it needs proving for these integrals. Yeah, it needs proving for these integrals. So the triangle inequality is this: that the absolute value of an integral of a function f of t is less than or equal to the integral of the absolute value. Okay, so you see this a lot in real analysis. You often kind of do it without even thinking sometimes because it's so elementary, this inequality. Okay. We will use it massively in complex analysis. All the time we will use it in complex analysis. Right? It's an extremely important and extremely useful inequality. Okay. So the proof goes like this. It's a short proof. Okay, but it's a real do I understand complex numbers proof. All right, it is really like that. Okay, so what we do is we let theta be the argument of the integral f of t dt, a to b. Okay, we start by letting theta be that argument. Okay, well, what does that mean? Well, that means that the integral from a to b f of t dt is r e to the I theta. Yeah, r e to the I theta. I can write it as r e to the I theta, where r is the absolute value of that integral. And I've just called the argument theta. Yeah, so this is now just saying that that complex number, well, on the left, the integral from a to b f of t dt, that complex number in exponential form is the absolute value times e to the I theta. Absolute value times e to the I theta. So, compare this with, you're saying that this is r e to the I theta here. Yeah? But r, of course, is always the absolute value. Yeah? That's the definition of r. Okay, so if that's true, then I can rearrange this. On the right hand side, I've got that absolute value. You see, yeah, on the right hand side, I've got that absolute value, which is what I want to kind of estimate. So that's equal to e to the minus I theta times the integral from a to b f of t dt. Now, on the right hand side, on the left hand side, I've got a real number. On the right hand side, I therefore must also have a real number. So if I write this as the real part, I should get the same thing, right? Because this is a real number. Okay, the real parts should be the same thing. Yeah, the real part of a real number is the number. Okay, and the reason is then, well, if I compare that to part one, yeah, see how the integral of a constant times a function is the constant times the integral. Well, that means that that integral is the real part of the integral a to b e to the minus I theta f of t dt. Okay, but equally, okay, and let's going backwards and forwards a little bit here. But if you look at that integral, okay, if I take the real part of this, yeah, I get the integral of the real part. yeah, I get the integral of the real part. So this is the integral from a to b of the real part of e to the minus I theta f of t. I'll put that in brackets so it's clear. We're taking the real part of all of that. Okay, and that's
Less
almost it, because that's then less than or equal to a to b, absolute value, e to the minus I theta f of t dt. Okay, because the real part is always less than or equal to the absolute value. Okay? And then on this thing on the right is the integral from a to b, absolute value f of t dt. Okay, it's the integral from a to b, absolute value f of t. Okay? Yeah. Minus I theta, because when you go from, if you go from here, from this line here, I've got the integral from f of t is the absolute value times e to the I theta. But on here, I start with the absolute value. So what I've done is I've moved the e to the I theta to this side to make it 1 over e to the I theta. And then that's e to the minus I theta. Yeah? So, yeah, so this is the absolute value is e to the minus I theta times this, and it's just rearranging that. Yeah. Okay. Yeah, this is a nice little proof. This is the proof that's in Alphonse's book. Okay. So there's not much more to say about that integral. Okay, the integral of a function from the real numbers to the complex numbers. It is defined in a certain way, and it does everything that you would want it to do. Okay. What we're really more interested in is the notion of a path integral, like we did or like you did in the first half of the module, where you're doing things like Green's theorem and other things that are important. You have to be able to parameterize and look at that. So these three definitions are the same definitions that you saw in the first half. Okay, so when I talk about a path, I'm really talking about a continuous function. So basically what I've just been talking about, yeah? A function that takes an interval but gives you a complex number. Okay, so it takes values in an interval showing and gives you a complex number. So, you know, the proper way to define kind of paths is as a continuous function. Yeah, continuous function. Okay, so I thought we I don't know. All right, so the path is a continuous function. Trying to escape. Path is a continuous function from the interval AB to the complex numbers C. Yeah, that's the idea. And then you've got to be careful about what you're really defining. So the trace of the path is the kind of the image. Yeah, the image of the thing. So it's the shape that is drawn. And then, you know, a set C is a curve if it is the trace of a path. Okay, so you've got all these definitions that sound very, very similar, but it's just being careful about what you really mean by a path. And the idea being that when you think of a path, yes, you think of a kind of drawing, but actually you should be thinking about a continuous function. Okay. There are various kind of definitions of these things, but we will come to that later on. So you learned about parameterizations in your first half. Okay, this, for example, is a parameterization. So we call the path, usually we call it a parameterization. Yeah. So when you have if you're going backwards, let's say, so see this, going from this third one, from a curve to a path, just means you have to actually work out what the function was. Yeah, which is, as you well know by now, is working out the parameterization. So if you had a curve like this, starting at this point and going like this can be parameterized by a function like this, p of t. Okay, so this is the parameterization from. So this is the parameterization from, I think it's 0 to pi to r2. Okay, so this is what you're used to doing, yeah. This is what you're used to doing. In complex numbers, it's the same thing, except that instead of writing it as a coordinate or a vector like that, you write it as a complex number. Right? You write it as a complex number like that. So P of t is sine 2t plus I cos t in this example. Okay. And there's plenty more examples. This is an interesting one. The curve parameterized by P of t is cos t plus I sine t is the circle, the unit circle, oriented anti-clockwise. The reason I've got this here, and this is not in the notes, the reason I've got this here is because how can you simplify that P of t? How can I simplify cos t plus I sine t?
Squaring it.
No, what's Euler's formula?
Oh, e to
E
the
to-
I
yeah.
theta. E to the I t.
It's t here, it's not it's t here, but it's e to the I. So this P of t is e to the I t here. Yeah? So this is kind of just a small kind of example just to show there are sometimes easier way, it looks easier basically in complex numbers. Yeah, it looks slightly easier. So the parameterization of the unit circle is e to the I t. Yeah, and then t goes from 0 to 2 pi. Right. Other examples, you've got an ellipse here. Okay, ellipses are kind of interesting in complex analysis because they're almost circles. All right, so this is an ellipse. If you've not seen the parameterization of an ellipse before, it's basically the same as a circle, except that you multiply either the x or the y by something, or both, of course, by something. Yeah, so this radius here, the major radius here is 2 and the minor radius is 1, which is reflected in the fact that you're multiplying the x bit by 2, so it's stretching it, but you're not multiplying the y bit by anything, okay, the imaginary thing bit. Okay. And again, it's going anti-clockwise like the circle did. So just to kind of say a little bit about this, you can simplify this in the same kind of way in terms of complex numbers. It is sometimes useful, so I will go through it. So the idea is that you can write cos of t is 1/2 e to the it plus e to the minus it, and you can write sine t is 1/2i e to the it minus e to the minus it. Okay, so these are just what we did in the first lecture. And then you can simplify this slightly, so you've got, if you so 2 cos t then is just e to the it plus e to the minus it. And then I sine t, okay, because this I is going to disappear now, isn't it? If you look at sine t here, if I multiply by I on the left here, that I is going to cancel out, and you get 1/2 e to the it minus e to the minus it. Okay. And then if you can add these together, so you've got 3/2 e to the it, what will be left over plus 1/2 e to the minus it. Right. So this is what an ellipse looks like, you see, in complex numbers. That's the only reason I'm going through that. Okay, the ellipse looks like this. Okay, e to the it plus 1/2 e to the minus it. Okay. Sorry. Okay, so working with complex numbers can simplify things. Things like this are easier to differentiate, you see. Yeah, easier to differentiate. Okay. Now the point of looking at these, same as in a real analysis, is that you want to be able to integrate along a path. Okay, you want to integrate a function along a path. So I'm going to kind of do a fairly swift description of this. All right, so most functions that we will look at will be continuous. All right, so it is a property of complex analysis really that the functions that you tend to look at are much well behaved, much better behaved than they are in real analysis. Yeah, so you don't have examples where they're differentiable in this bit but not in this bit, and it's continuous here and not continuous here. They tend to be much better behaved. Okay, and that's just the nature of the holomorphic function, right? It is just better. I mean, and it comes with its pros and cons. That does, yeah. If it's because they're so well behaved, they are less applicable. So things like physics and things don't naturally come up with holomorphic functions because they're just too nice. Yeah. But equally, they have their own uses in terms of understanding analysis and on manifolds and things like that. Okay, which are surfaces, I should say. Okay, so it's pros and cons. So anyway, so we'll talk a little bit about. The reason I said that is because for a continuous function, the Riemann integral and the Lebesgue integrals are the same, of course. Yeah. So everyone knows that. Yeah. So the Lebesgue integral and the Riemann integrals are the same if it's continuous. Yeah. I mean that's about as good as it gets. Yeah, because the point of Lebesgue integrals is that they allow you to integrate a broader class of functions. Yeah, that's all they're doing. It's not like I know we kind of joke about the fact that you're in your third year you're taught that everything you learn about integration is wrong. It's not that. It's that Riemann integrals that are fairly easy to define functions that you can't integrate. Yeah, and that's a problem. Okay, so the Lebesgue integral, although it's awkward and difficult to define, it is there because that's kind of as good as we can get, yeah, in terms of integration. And the class of functions you can integrate then is more useful. Okay, but for complex analysis, we don't need that. We only need the Riemann integral. So you define these things. So the definitions look a lot like the definition of a Riemann integral. Right, so if you remember the Riemann integral, if you integrate along an interval, what you do is you partition the interval, and then you work out what it is at different points, and the idea being that as the partitions get smaller, your integrals converge. Okay, it's essentially the same thing in complex analysis. So I'll kind of hand wave through this a little bit. Okay, so the idea is if you want to integrate along a curve like this curve C here, what you do is you partition it into different points. Okay, then between each of these points, what you do is you take the value of the function at, let's say, the first point, and then you multiply it by the next one minus the first one. Okay, so the integral here would be f of z5 times z6 minus z5. And those give you values, and the idea being that this is an approximate value of what the function is multiplied by the size of that kind of partition, really. Right. So that's the idea. Then what you do is you do that for all of the points. You sum it up, and that should be an approximation of your integral. Okay. In general, if you take a partition like that and define that sum, the idea is that if you've got some number I, a complex number I, so that whenever there's an epsilon, you can find a partition so that the sum of this partition thing minus I is less than epsilon. If you can do that, then I must be the value of the integral. Okay, so this is basically Riemann integration. Okay, this is Riemann integration. Now there is a Lebesgue version of this. Okay, there is a Lebesgue version of this. If you take your curve C, okay, the idea is a similar kind of thing. Okay, and this is now getting beyond the scope of what you've done in Lebesgue measures. Okay, the idea is you do a similar kind of thing. Okay, for Lebesgue, so this should say Lebesgue version. So just to say, and the idea being that you can measure sections of this curve. Let's do it in red. You can measure sections of this curve. So let's call it Z. W, and then let's call this C of ZW. You define this measure on subsets like this ZW to be equal to Z minus W. Okay. That's the idea, is that you define a measure on it, and then if you integrate with respect to this measure, then you get the same thing. Right? So there is a Lebesgue version, there's a Riemann version. We will only need the Riemann version because all of our functions are going to be continuous. They're actually going to be differentiable. Okay. So just to kind of, I don't want you to think that you've spent 6 weeks learning about Lebesgue measure and we're not going to use it. Okay. We will occasionally see it or used and so on. Okay, so here comes the definition. The definition of an integral along a path is the same as you see when you differentiate vector fields in Rn, okay, with along a path. Okay, so it is that you should be thinking about. Okay, so suppose you've got a parameterization of a curve, okay, P of t between A and B, then you only need it to be differentiable almost everywhere. Okay, so it's differentiable everywhere except a bunch of points, basically. Okay, or piecewise differentiable, you've seen that, called that as well. Okay, if that's true, then you can define the path integral, the integral of f of z dz along C, to be the integral of the parameterization. Okay, so the integral goes from A to B, so this is the bounds for your parameterization. It is the function defined at P of t multiplied by the derivative. Okay? So this is similar to the stuff that you saw when you integrated vector fields. Yeah? When you integrated vector fields, you take the dot product, but dot products in the equivalent of a dot product in complex analysis is multiplication. Yeah? So multiplication is an equivalent of dot product. All right, so just do an example. It's worth doing an example of these things, just to see how these things are done. They're fairly straightforward, and they're fairly straightforward if you've got the parameterization. Okay, working out the parameterization is less straightforward sometimes, but it is nevertheless doable. Okay, so
what's the difference between dot product and multiplication?
So, well, if you think of, you know what, in complex analysis, if you think of complex numbers as a vector, yeah, like a coordinate, yeah, then multiplication and multiplication of complex numbers is kind of like a dot product there. Okay, I mean you have to work through the algebra, but it's a similar thing. Okay, yeah, I will just write it down. So if you take ZW in the complex number, I'm going to delete this almost immediately. Okay, no, let's actually instead. It is worth telling you this just to kind of give you an idea of what's going on. Suppose you've got Z is equal to A plus IB, W is equal to C plus ID. Okay. Okay, then in the vector versions of that would be AB and CD. So the idea being that if you take the dot product of these on the right, you can look at what the equivalent is. So the dot product is AC plus BD. Okay. Now, if you take Z times W bar, okay, bear with me for a second. If you multiply Z times Z conjugate, W conjugate, you get this. Okay, so it's AC plus BD on the left there, plus I times BC minus AD. Okay. So the point being that if you look at the real parts of that left-hand side, okay, real part of Z times W is AC plus BD, which was the dot product. So I'm just showing you, this is, you know, there is a link, there's always a link between R2, vectors in R2 and things like multiplication in complex numbers. So, yeah. For those who did function analysis, this is the inner product, yeah? The real part of ZW bar is the inner product.
Mohammed did function analysis.
We did do function
How was
analysis.
it?
Sorry, you for. He didn't do function analysis, so we did the whole stuff about inner products. Okay, so anyway, let's go back to the example. So to calculate this, okay, you need the derivative. Okay, so the derivative of t plus t squared I is what?
2t.
Where's the t gone?
1 plus 2t.
Yeah, 1 plus 2t. The reason I'm asking is that, you know what they are? People are kind of afraid when they see I sometimes in a number. When you differentiate something like this, you treat I like it's just another number. Yeah, just treat it like another number. Even when you do differentiate things like e to the it, you still just treat it like it's another number. Yeah, don't worry about that. Yeah. Okay, so p dashed of t is that f of p of t then is equal to 2 times t plus t squared I, which is 2t plus 2t squared I. Okay, and the reason is, of course, because I want to work out this. Okay, so the definition of this, let's go back to the definition. The integral along that curve C, f of z dz, is the integral of f of p of t multiplied by the integral multiplied by the derivative, sorry.
So that's 2t plus 2t
So
squared times.
That's right. So you've got this is f of p of t,
Yeah. Multiplied by the
and this is what was it? 1 plus 2. Yeah. So this is, you know, it's just standard stuff that you've seen before, and now this is an integral of the form that we've just been looking at, the integral of a function taking an interval to the complex numbers. Do you need to kind of work this thing out? So if you expand this, you get 2t plus 4t squared I multiplied plus 2t squared I plus 4t cubed I squared. Okay, and I've got no room for the dt. So this I squared, of course, becomes minus 1. Yeah, so I'll delete that and just put minus here. Okay. So this then is the integral minus 1, 1. If you take the real parts, you get 2t minus 4t cubed dt plus I times the integral from minus 1 to 1. The imaginary parts, you've got 6t squared, isn't it? 6t squared. Okay, so the first integral is 0 because those are odd functions. Yeah, those are odd functions. To t and t cubed are odd functions, so that is 0. Yeah, and the integral of 6t squared from minus 1 to 1 is 4. So it's 4i, the answer anyway. Okay, so the integral is 4i. So yeah, the first is 0 because those are odd functions, or you can't just work it out. Yeah, you can just work it out. And then this integral of 6t squared is 2t cubed between minus 1 and 1, which is 4. Okay, so that's path integrals for you. Okay. So we will check, you know, we should check really that all of the kind of properties that you learned in the first half still apply. So things like when you take a curve but you change its orientation, then the integrals should be a negative of each other. Okay? And remember, in the first half, when you do that, we write your kind of curve in the opposite direction as minus c. Yeah. So if c is a curve in one orientation, minus c means the same curve but oriented in the opposite direction. Okay, so for example, if that's c, okay, that's heading that way, c heading, this is minus c, heading in the opposite direction.
So it just means if we kind of swap all the limits of integral, then the sign change.
Yeah, so you have to swap the intervals, you have to write, instead of p of t, you look at p of minus t, or something like that, okay? That's one way of doing it, okay? You also have, and this we will use willy-nilly, okay, that the integral of the union of two curves is the sum of the integrals. Okay. So all of these should work, and again we should check that the integral is independent of its parameterization. Now you proved all of these in the first half, and I don't want to do it again. Okay, I don't want to do it again, so I'll just prove this. All right, and we will use this. We'll use this quite a lot. And I'm going to prove it with a little bit more detail on this in the notes. Okay, so suppose the idea is you've got a function that takes complex numbers to complex numbers. Okay, and we're going to do this Cauchy-Riemann thing where we write it as f of x plus iy is uxy plus ivxy. Okay. Now, what I want to do, the point of this theorem is, or lemma is really in those, but for some reason I called it theorem. But anyway, so the point of this is we're going to just link complex parameterizations to real parameterizations. And the point is then I don't need to prove all that stuff again. Okay, I don't need to prove all that stuff again. So it turns out that the integral of a function f of z dz can be written as two integrals of vector fields. Yeah, vector fields. So the first integral along a dot dr, which is the stuff that you've done in the first term, plus I times the integral of b dot dr, and they are particular vector fields. Yeah, the vector fields are these things. So A is the vector field where you've got u in the first coordinate and minus v in the second coordinate. And B, you've got v in the first coordinate and u in the second coordinate. Okay. So it's kind of, the b's have swapped over. Okay. Now to prove this, you simply just need to actually do some calculations. Right? And start from the left. Okay, so start from the left here. So work out what the integral of f of z dz is. Okay. Now, so here we go. Integral from f of z dz. Well, if I write that as the integral from c to d, so the parameterizations here go from this will be f of p of t times p dashed of t dt. Okay, so I'm going to need lots of room here. So the idea is that f, okay, f is this u plus iv, of course. That was supposed to be a line. I didn't do a line. Okay, so f of z, actually let's call it x plus iy, is u of xy plus iv of xy. Okay, so if I have written the first coordinate, if you like, okay, if you look at the way I've written p of t, okay, if I look at the way I've written p of t, I've written as p1 plus I times p2. Okay, so the real part is p1 and the imaginary part is p2. So if I want to work out what f of p of t is, that is u of p1 t p2 t plus I times v p1 t p2 t. Okay, and I'm multiplying that by the derivative, and the derivative is p1 dash of t plus I times p2 dash of t dt. Okay. And again, you know, this is just complex numbers. I can just expand these. I'm going to do it relatively quickly so that, but you can, you know, if you need to, please check it. This is an integral from c to d. So if you look at the real parts, to get a real part, if I multiply these two things and I want to get a real part, it's this times this plus, minus this times this. Yeah. So it's the real parts here. And you know, normally when you'll get another real part when you multiply the I bits of both of them, yeah. So
And because I squared is minus 1.
and because I squared is minus 1, you get a minus there, yeah. So you get u of p1t, p2t times p1 dash of t minus v of p1t, p2t, p2 dash t. So that's the real part. And then you've got the imaginary part. Okay, so the imaginary part is easier, yeah, because you get one by multiplying this by this, and you get another one by multiplying this by this. Yeah. So so let's do the first one. You've got v of p1 of t, p2 of t, multiplied by p1 dashed of t, and then you've got plus u of p1 of t, p2 of t, multiplied by p2 dashed of t. Okay. Now then, so if you look at the first integral, the real part, okay, I've got u times p1 minus v times p2 dash. Sorry, u times p1 dash minus v times p2 dash.
Now, is that a P1 or a P2 to the right of the V? Sorry, I can't really read you.
P2.
No, second line down. Just
That's
after
P2 as well.
This one at the end.
P1.
No, this one.
V of P1
V of P1.
and
right,
P2
yeah.
and then P1, yeah.
Right, okay.
So this is the integral from c to d of, and I'm going to get rid of these I'm going to get rid of these t's for the moment, okay? But take, you know, u to be u of p1, p2. Just because otherwise I'm going to run out of space on it. So it is the dot product of v u p1 dash p2 dash. Okay. And that's it, because this was my vector. This is what I said the vector field was going to be, and this is what I said the vector field was going to be. Okay, this is what I said the other vector field was going to be. So this I would call A, just for now, and this I'll call B, the vector field A and B. And this is really useful now, because basically what we're saying is that I know, I'm not going to have to prove any of that stuff, because I can rewrite parameterizations in the complex plane as parameterizations in R2. All of that stuff that you've done in the first half of the module will then move over to the stuff into the second half. Okay? So that's the idea, okay? That's the idea. We are also going to use it in a more important way after the reading week, okay? It's not just a mechanism for doing that. Okay, so as a consequence, we basically have everything that we wanted. Okay. Okay, I might skip some of these examples because do you want to have a break for 5 minutes?
Yes.
Should we have a break for 5 minutes, all right?
Have a brief.
Have a brief. I want to, yeah, because I knew it was